Okay, so I wanted to pick back up and do a couple of things, and also look a little bit more in detail about this whole breadcrumb thing, and maybe explain that a little bit better, or again. Um, the first thing I want to start with, though, is a little bit more about the arithmetic situation. Um, so let me get this shell started. Okay, so great, we've got our usual shell. So for the assignment, what is it, B, I guess? Well, first off, did A go okay, the arithmetic by hand? Yeah, sort of getting there. Okay. So the point of, and for right this moment, really want to concentrate on the, say, the third problem, right? Where you were taking a 16-bit number and adding it in 8-bit chunks. And the only reason I chose 8-bit chunks and a 16-bit number to do it by hand was just to keep the sizes of the problem more manageable. Okay. Um, that, by the way, would be how a computer from the 80s would have to do 16-bit arithmetic if it only had an 8-bit um, arithmetic processing unit, or arithmetic and logic unit, or ALU for short. Okay. Um, but the premise of it is the same, where for assignment B, where, well, we could do 128-bit arithmetic by doing it as a pair of 64-bit chunks, right? And you could imagine doing 128-bit arithmetic with, I don't know, what would it be? 16 8-bit chunks. You just have to kind of keep going and going and going, and it would be tedious. Yeah, we don't have to on this machine, of course, because we've got the ability to do 64 bits at a time. But if we wanted to, for example, um, code 128-bit arithmetic on a 1980s computer, it would have to do it in 16 steps. Okay, and as you can imagine, that would start to get kind of slow. Um, okay, so there's sort of two issues to deal with the arithmetic. One is just loading the damn numbers into the registers in the first place. Okay. Now, if the number is relatively small and easy, you can just do it. So, for example, um, let me just say something like this, right? I can load x0 with the number 0, and I can do that with a single instruction. Okay. But what I cannot do, and maybe you guys have discovered this the hard way, is something like this. Okay. You cannot do that with a single instruction. Um, and let's think about why you can't do it with a single instruction. Well, how big is this number and uh, feed K dead beef, right? How big is that number in terms of the number of bits? It's a 64-bit number, right? But the instructions in 64-bit ARM, how wide is each instruction? They're all 32 bits, okay? And I would have to encode within those 32 bits both the fact that I'm loading a number into a register, and I would also have to specify, well, which register, um, but then I would also have to specify the number. Well, I can't fit 64 bits plus some extra crap into a 32-bit link. Like, you just can't do it. Okay. So this instruction, move x1 feed k dead beef, will not work. Okay. And in fact, if we try to assemble it, let's see what the error message that we get. Okay. We're going to get this, the error, immediate cannot be moved by a single instruction. Okay. So that instruction, or sorry, that number is too big to load in a single pass. Okay, well, that's annoying because we want to have the ability to load any number into a register. So what do? So there are two options. Okay, one is to define that number up here in our data section, okay, in advance. And so let me call this just num1. And then what kind of number is this? It's a long integer, okay? That's what we would have called it in C. But what do I have to put in my assembler preprocessor here? I have to put D word for double word, okay? So what's a word is a 32-bit quantity, or well, 32-bit chunk of data, right? The word doesn't necessarily represent it, like that data could be a floating point number, it could be an integer, it could be a part of a string. It's just a chunk of 32 bits. You're not, you're not really caring what it encodes at that moment. And what is the number? Well, let me just type it back in, feed K dead beef. Okay, so I could do that. And then down here, I could, instead of loading X0 with, I could load X0 with the memory address of num1. And then I could load X1 in direct reference to what's in X0, okay? So what is this, what do the brackets do here? The brackets do indirection or indirect reference. So what I'm telling the machine is, okay, go over to mailbox X0, and the number that you find inside is a mailbox number. Go to that mailbox with the corresponding number and grab whatever's in it and put that number into X1. Okay, so I think didn't Tuesday last week I kind of gave the analogy of my parents, their mailbox situation at their house, right? They don't have a mailbox out front of their house like a lot of places do. Okay, so that's certainly one way to do it. Okay, okay. So if I run this or assemble it, then we get no errors, and we could link this and execute it, and everything would work fine. Okay, so if the number is big, then you have to resort to doing something like that. Okay, now let me give a second example, which is, what about if I wanted to load all F's? Okay, what is all F's? It represents -1 as assigned integer. So could I do the following? Let's just put it in X2. Let's do -1. Okay, that works. And you might say, well, wait a minute, Dr. McKinney, why should that one work but not this one? Because what's the difference between all F's and feed Kate dead beef? Right? They're both really long with lots of ones all over the place. Okay. And the reason is that the move instruction is not actually an instruction. It's a pseudo instruction. Okay. So what I mean by that is that when the assembler encounters move, it replaces it with, and if any of you happen to have your ARM cheat sheet with you, grab that, because that'll be kind of useful for right this instant. So remember this thing from on the exam. So if you happen to have that handy, look at it real quick. Okay, so if you look at the sheet, you probably notice that there's some of the instructions that are slightly italicized. Okay, those are the ones that are pseudo instructions. Okay, so for example, like the comparison instruction, it's really a subtraction instruction. Okay, but you don't really think about it that way. You think of it as a comparison. Okay, so if we look, for example, on the the first page, the top middle box, okay, of the thing, and we look at move, we actually see um, that move, okay, either immediate or register to register are both pseudo instructions, but the true move instructions are move K, move N, and move Z, okay? And we'll talk a little bit more about them, but basically, let me do the following, and I'll do it to X3 so that we can do a comparison here. Okay. And so I'll do, just humor me for the moment, and we'll see why this works in a second. I'm going to move x2 -1, and I'm also going to do move in x3 0. So if you look at that instruction, what do you think is going to end up in x3? Just looking at the way the instruction's written. Okay, and yeah, because I typed 0, so why wouldn't 0 end up there? Okay, what will actually end up there is -1. Okay, and here's why. What is 0 encoded in 64 bits? 64 zeros in a row, right? What would happen if I logically knotted each of those bits? All the zeros would turn into all ones, okay? Or in hex, a 0 would turn into an F, right? So if I've got 64 zeros in a row and I flip all of them, they turn into all ones. Well, guess what that is? The encoding of -1, okay? So this N here stands for negation, or sorry, not. It does not stand for negation, okay? Okay, and that hopefully you guys noticed on the paper assignment. How do you negate, in an arithmetic sense, a number in 2's complement? You do the ones complement, which is flipping all the bits, and then you add 1, okay? The move in instruction flips all the bits. It doesn't add the 1, okay? So this is why I put 0 here and not the number 1, okay? Because I'm not doing the add 1 part, okay? Or this instruction doesn't do it. Okay, is that okay? All right, so let's run this and assemble it. And let me actually get a listing file while we're at it. Okay, and let's open up that listing file for a moment. Okay, here. Okay, and what I want you to notice, okay, is that these are actually doing the same instruction. Okay, now how do I know that they're doing the same instruction? Well, what did I type? I typed move for one of them and move in for the other. Yes? So it looks like I've done different instructions, but let's look at the actual instruction encoding. Okay, what's different and what's similar? Okay, the 2 and the 3 are the only things that differ. Well, does that make sense looking at the instructions? Why? Yeah, one of them's going into register 2 and one of them's going into register 3, and it's sort of coincidence that we can just humanly read this. Because well, for technical reasons. But the opcode here, in terms of the encoding of the operation to be done, okay, is basically being described down at this end, 9280, and the order is a little backwards from how it shows up. Let's not worry about that at the moment, okay? But they're the same opcode, right? Which means these literally are the same operation for the machine. The only difference is which register we're going into. okay? So when I typed line, well, I guess it's 14 here, right? What the assembler did is it actually replaced the instruction with um, move in x2 0. Okay. Now it didn't change that in my the actual assembly code that I typed, just to be nice to me. But in terms of the actual encoding of the instruction on the machine, it's really more like line 15 than it is line 14. Okay. All right. Is that okay? So let's actually run this and make sure that we end up with -1 in both registers, just to make sure that it worked correctly. And so let's see. All right, so we need to, oh, and I need to go back and add in the debugging stuff so that I can do, so that we can go into GDB. Okay, so both instructions have executed, and lo and behold, what do we see in the various registers? What ended up in register 0? Yeah, the memory address where feed K dead beef starts, okay, which happened to be 48A048, okay, whatever. The number that ended up in X1 was feed K dead beef, okay. And what ended up in both X2 and X3? -1. Okay, so if you were trying to load, so like some immediate numbers you can load, you can just do them, okay? For example, if I wanted to just load the number 5 into a register, right, that's no problem, excuse me, because 5 only takes what, a few bits to, right, it doesn't take all 64 bits to encode that. There's a lot of leading zeros that you can just sort of chop off, okay? So small reasonable numbers, ones that say are 16 bits or fewer roughly, can be just done, right? No big deal, okay? But what instruction they're actually using is one of either move K or move Z. Okay, so what move Z does is it basically zeroes out the register before it starts loading things in. Okay, so for example, what is in X3 at the moment? Yeah, -1. Okay, so a whole bunch of F's, right? So let me go back to the code and let me add an instruction here, and then let's compare what it does. Okay, so I'm gonna just, oops, I can't do it in the listing file. I need to do it here. Okay, so let me do move Z X3 0. Okay, and then let me reassemble everything, and let's go back into GDB. Okay, so what's in the registers right now? It's exactly how it was just a minute ago, okay? And I am about to execute the move Z X3 0 instruction, okay? And if I step one more time and then look at the registers, what's in X3? All zeros, okay? It zeroed it out before it loaded in the number 0. Okay, now that's maybe not very convincing as to what's happening. So let me actually quit and change the instruction um, to move K. Oops, too many terminal windows. Okay, so same state as before. I'm about to execute this new move K instruction. What do I see in X3 before I do this? All Fs, right? All ones. Okay, if I step one more time, step one more time and then do it, what's in register X3 this time? Okay, I loaded in 0, but I preserved all the bits, the other bits of the register. Okay, so what this basically shows us is what's the largest number of bits that you can load in a single instruction? 16 bits. Okay, and if we think about it, that kind of makes sense, all right, for two reasons. One, it has to be smaller than 32 bits, right? And it has to be genuinely smaller than 32 bits because we have to spend some bits on the encoding of the damn instruction in the first place. We have to specify which register, we have to specify what operation we're doing, okay? And for that matter, how many bits does it take to specify which register? Or how many registers are there anyway? 32. So how many bits does it take to do that? How many bits does it take to encode 32? Huh? 5, right? 1, 2, 4, 8, sorry, 6. Okay, 6 bits, right? Okay, now it's actually only 5 bits because there are 32 registers, but the last one is sort of weird and special, so that's like, from our perspective, there's really only 31, and therefore we can get away with 5 bits, right? Okay, so if we have 32 bits to encode an instruction and we spend 5 even just specifying which freaking register to use, well, there's 5 bits gone, okay? And the instruction itself needs some bits, and there's a few other things. So upshot is you can only basically do a 16-bit immediate value. Okay, now, so what's the difference between move K and move Z? Move Z zeroes it out before you load anything in. Move K loads the bits that you're specifying in and overwrites those target bits of the register, but anything that's not overwritten stays as it was before. Okay, this means actually that we could load in feed K dead beef basically in 4 16-bit chunks. Okay, but there's one other thing that we have to deal with. Where did the zeros end up here? Which 4 or which 16 bits did they end up in? The lowest 16 bits. What about if I wanted them to be in the next 16 bits? Perfectly reasonable, right? Okay, how would I do that? Well, how might I do that? Okay, so this is maybe a rhetorical question at this moment, but what kind of operations can I do with bits and registers, right? We can add, we can subtract, and yes, eventually we can multiply and divide, right? We can do all the usual arithmetic operations. Okay, but what's another operation that would be really, really handy to have? Okay, this may go back a little while, but did I ever tell you guys, maybe not in this class, I've had some of you before, but did I ever tell you guys the story about when I worked at Kohl's right after Christmas? Okay. Did I tell you guys in this class? No? Okay, well, so then what's the story about me working at Kohl's? Okay, yeah, decimal places. So, lady comes up to me a couple days after Christmas and says, um, is all of this stuff 90% off, right? Because after Christmas, we want all the stuff gone. So she hands me some like thing, decoration, and I'm like, yes. Okay, well, in retail, what's the hardest question to answer? When they say 90% off, well, of what? What's the sort of rule, if you will? They always mean off the original price, which is the price that's actually printed on the sticker or the label. Okay. Nobody ever actually pays the full sticker price. That's the other law of retail. Okay. Okay. So I flip the thing over and I find the tag and it says $30. And so how much does it cost? $3. Right? Okay. No big deal. So how did I do that so quickly? Well, I divided by 10, but dividing by 10 is the same thing as moving the decimal point, okay? Or maybe another way to think about it is because I don't really need 30.00, I just shifted the digits by one position, okay? So in addition to adding, subtracting, multiplying, dividing, those kinds of things, or logical operations like and or not and so on, what else would be really handy to have? Bit shifting. Okay, so I can get those zeros into the next 16-bit chunk if I shift. Okay, and if you want to have a fun drinking game, try and say bit shifting after you've had a few. So, yeah, so I can bit shift, or as Dr. Brown sometimes likes to call it, bit banging. Okay, um, but make sure that you have, let's just say, acknowledgement from both devices, uh, and the appropriate permissions are present before you do any bit banging. Okay, um, yeah. Okay, so let me go back to the code. And in this move K instruction, I'm going to add in um, an optional thing, and I'm going to add in, well, let me just say 16. Okay, so it looks like I may be loading and trying to load in two numbers, but I'm not. The syntax for this is that the 16 is how many bits I want to shift the number by. Okay, and I'll show you how this works in a second. So let me quit this and let me go into here. Oops. Oh, yes. So I need to do LSL. Okay, what do you think LSL stands for? Well, what does the S stand for? Shift. Okay, store, shift. Yeah, both reasonable guesses. It's shift. Okay, what kind of shift am I doing? I'm going which direction? Left. Okay, and it's a logical shift, meaning I'm just moving bits. Okay, there are other kinds of shifting. There's arithmetic shifting and rotating. Okay, but I'm doing a logical shift to the left, and this actually, since I'm hovering over the instruction, VS Code is being very nice to remind me. Well, what does move K actually stand for? Move wide with keep. Okay, there's the keep part where only some of the bits got overwritten, but the rest of them got left alone. Okay, so let me go ahead and reassemble this and let's go back into GDB. Okay, and as before, this is what we had, right? Negative ones in the thing, all F's, great. And I'm about to execute this move K instruction where I've added this logical shift. Okay, so where should the zeros end up when I do this instruction? Are they going to end up in the lowest four nibbles corresponding to the lowest 16 bits? No, they're going to be in here, the next 16 bits, because how many bit positions did I shift by? 16, and I went which direction? Left. Okay, so let's step it and look at the registers, and ba-bam, where are the zeros? where I said they would be. Okay. All right. So let's take this lesson, okay, and actually load in feed K dead beef the other way that we can do it. Okay. And so let me do this. What are the last 4 nibbles? Okay, so the last 16 bits, the lowest 16 bits of feed K dead beef. Beef. Okay. So what I will do is I will start with a move Z and beef instruction, or loading beef in. Okay. So the Z will take the register and zero it out, and then put beef in the lowest 16 bits. Okay. And then I want to move K, but what's the next 16 bits I want to do? Dead. Okay. So I'll replace this with 0x dead. Okay. And the reason that I want to use move K here instead of move Z is because if I used move Z, what I would end up with is a bunch of zeros, dead, and a bunch of zeros. And I would destroy the 16 bits of the beef. Okay. But move K keeps what's already there and only overwrites the 16 bits that I'm specifying. Okay. So, which of course is what I want. And then I could do this 2 more times. All right, what's before dead? K'd. How many bit positions do I need to shift this time? 32. And what was before K'd? Feed. And then it would be a 48-bit shift because, yeah. Okay, does that make sense? All right, so let's assemble it and run it and see if it works. Okay, so I'm about to load in the beef. Okay, which I know sounds a little ridiculous, right? I mean, if you can put things in hex, right, you might as well have some fun with it. And the other reason that I decided to feed Cade dead beef is, of course, last year Cade was actually in the class. And so it seemed apropos that Cade might want some dead beef, right? Speaking of which, I still owe you two some dead beef, right? Um, okay. All right. So what happens to be in register X3 before I start doing any of this? It just so happens to have 400608. Okay. Whatever. There was something in that register before my program started. Fine. This is why I'm going to cover my butt with that move Z instruction and kill all of it. Okay. So if I step and I just executed the beef loading instruction and I look at the registers, then beef is there, and what's in all of the bit positions to the left of the beef? All zeros, okay? And so GDB is not going to actually print all those extra leading zeros, but they're still there. Okay, is that okay? Yeah? Okay, so I've got beef there. And then if I step one more time and I just executed the moving and the dead part, and then what do I see? Dead beef. Okay, and if I step and I look at the registers, what do I see? K dead beef. And if I step and look at the registers, now I've assembled all the way up to feed K dead beef. Yeah? Okay, so how many instructions did it take to do all of that? To get the feed K dead beef into register X3. Took 4 instructions, right? Because I was doing it in 4 16-bit chunks. How many instructions did it take to get into X1? It only took one instruction there because it defined it as a piece in my data section. Okay, so this sort of begs the question then, why might I have to do this sort of 4-step process to get this immediate into a register when I could have something in my data section? Well, better late than never, man. Well, one is, what about if I didn't know that the number was actually feed K dead beef from the get-go? Right? I picked that number in advance, but let's say I'm writing some program and that number is, I don't know what it is in advance. Okay, well, so there's one reason. I may not know what the number is from the get-go. And then the other is, well, what's faster, using memory or using registers only? Registers only, okay? So, yeah, but you've got two ways to do it, right? Loading immediates with the shifting, okay? Or defining the word or double word in your data section and then kind of going from there, okay? So either method will work in order to get sort of seemingly too large immediates into into the registers where they need to go, so that you could then do arithmetic with them, like adding and stuff. Which brings us to our next topic. Okay. Okay. So let's take the number. Okay. Um, so let me just take what happens to be in registers 2 and 3. Okay. What was in register 2? It was all Fs. Okay, now how should we interpret that bit pattern? What does it represent? It represents -1 as a signed integer, or a really, really big number is an unsigned integer. Okay, so what would happen if I think of all F's as being an unsigned integer, and I add 1 to it? Well, signed or unsigned, it actually doesn't matter here. It'll turn into 0. Okay, and that kind of makes sense because if I think about it as a signed integer, this is effectively doing 1 minus 1, right? And last time I checked, 1 minus 1 was in fact 0. Okay, but what technically is also happening if I add 1 to a bunch of F's, which is like 64 ones in a row? I do the addition, I'm getting a bunch of carries, carry, 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 and then what do eventually I get? A final carry that would go into the 65th bit position. But is there a 65th bit position? No, there is not. So where does that 1, that carry, go? If there's no 65th bit position, where does it go? It either disappears completely or goes into the processor status flag for that there was a carry. Okay. And how do I know which one is it going to be? Well, that depends on which add instruction I use. Okay, so let me go back into our code and let's add, and let's put the answer in register 4 just for demonstration's sake. And what am I going to add here? I'm going to add well, here actually, let me put the number 1 in X4, and then I'll add X5 will be the destination, and I'll add X4 and X2. Okay, so what this is basically asking, what's 1 plus -1? Right? What should end up in X5 after I execute all of this? Should be 0. Okay, but a carry will have occurred. Okay, and so let me assemble it, run it, and do you guys mind if, just for sake of demonstration, I still need this one. I just I'm going to comment these out just so that we don't have to step through as many instructions. That'll just save us a little bit of time. Okay, so right before I execute the instruction, let's look at what we have. I have in register 2, I have -1. Okay, in register 4, I have 1. And in register 5, right now, I have gobbledygook. Okay, and I'm about to execute the add instruction. So if I do that, also, before I do so, what are the flags that are raised? So the flags for this, I'm looking down here at CPSR, okay? This is the processor status register, and I see the C and the Z are flags that are raised, okay? So what are the 4 flags that we care about? C stands for carry, Z stands for 0, V stands for overflow, and N stands for negative. Okay, so if the result of an operation, a flag setting operation, is negative, 0, or whatever, then the appropriate flag will get raised. Okay, so if I do this add instruction, should the carry flag get raised? Okay, but it won't. Okay, and the reason is the add instruction does not set the flags. The add S instruction does. Okay, so here, let's step and then do the registers. Okay, after this operation, what happens to be in register 5? 0. It was supposed to be. Okay, so that's good. Okay, but what happened to the flags? Did they change? No, they didn't change because the operation I just did not set the flags. Okay, I would have to change the add to be add S. Okay, so let me do so. Oops. There we go. Okay, so let me change this. And actually, for sake of demonstration, would you guys be so kind as to humor me and let me put the number 2 here instead of 1? Okay, whatever, doesn't really make a difference. But there's a reason I wanted to do that. Oh, and I want to change this to the add S instruction so that it does set the flags. Okay, so right before I do the instruction, so I've loaded in the numbers into the registers. What's in X2? -1. What's in X4? 2. Okay, and so what's going to happen when I add them? Well, what should I get? 1. Okay, but does the result of that operation, did a carry occur? Well, okay, let me rephrase. Will a carry occur? Because I haven't actually done the operation yet. Yes, it will, okay? Because if I add 2 to this big long string of 1s, I'm going to get a crap ton of carries, and then I'm going to get a carry at that final bit position. Yes? Okay, so a carry will occur. Now, it just so happens that the carry flag is already set. Okay, so if it's already set and I raise it, it's not going to look to us like anything happens. Okay, however, what about the 0 flag? Is it currently set? Is the 0 flag currently raised? Yes, because it's there. Okay, what is the result of the operation I'm about to compute? Negative 1 plus 2. 1, not 0. Okay, so what should happen is that the carry flag will get raised. Now, it just so happens to already be raised, but the 0 flag will get cleared. Because is the result of the operation I'm about to do 0? No. Okay, so let's step and see. And ba-bam, what's in register 5 now? Is that number 0? No. So what happened to the 0 flag in my processor status register? It's gone. It got lowered. Okay, so that actually corresponds to a bit of, well, 0. Okay, and if the bit is a 1, then the flag is raised. Okay, so the difference here, right, is the add instruction does the arithmetic, but it doesn't set any processor flags. Okay, the add S instruction does. Okay, now, when you guys did the arithmetic by hand, which instruction did you use for the lowest place value? Like, what basically were you doing? You were really using add S because you did the addition, but there might have been a carry that you had to take to the next chunk. Okay, does that make sense? Now, for the second set of place value, what instruction were you using? Well, it's not just add S because you had to take into account the carry that may have occurred in the previous operation, right? And that operation is called add CS. Okay, so let me change the add S to add CS. And let's see what happens. Okay. Oops. Oh. Okay, so I'm about to execute the add CS instruction. All right, what is in registers 2 and 4? Negative 1 and 2, and look at the status registers. What flags are raised? The carry flag and the 0 flag. Okay, so what is the operation that I'm about to do? I'm about to add registers 2 and 4, right? Okay, what is in register 2? Negative 1. What's in register 4? So what answer should I get? 1. But I don't. I get 2. Why? What was the carry flag before I did that add instruction? No, it was a 1. The carry flag was set before I did the add instruction. Yes? Ah, okay. So the carry flag was set, and so when I did the add instruction, add CS takes into account the carry flag. So what it did was it did negative 1 plus 2 plus the carry flag. Well, if the carry flag is a 1, which it was here, then that's where the extra 1 comes from. Okay, does that make sense? No, it's add CS. Okay, so it just so happened that when we did this, when I ran the program, right before I did that add instruction, the carry flag happened to already be set. Okay, so which I needed to worry about. Okay, so well, what were the numbers that I had you guys do by hand? It was what, A, B, C, D, and 9876. Okay, and if I take those in chunks, then you add this chunk you would do with an add instruction. Okay, what was the sum of CD and 7.6? It was 4.3 if memory serves. Yeah, 4.3 with a carry. Okay, this next instruction, I need to do add C or add CS. Okay, and the reason that I could choose either one here is because does this place value need to take into account the result of a previous carry? Yes, right? That's where that extra one would come from, okay? Does the final position need to set the flags? Doesn't need to, but go ahead and do it, okay? So use the add CS for the final instruction, okay? So if I want to add, so for the 128-bit numbers, what am I going to do for the lower 64-bit chunks? Which operation am I going to use? Add S. Set the flags, but don't care about what they happen to be beforehand. For the next chunk, what am I going to use? Add CS, because I do care about a previous carry. Okay, and then if there is a final carry in that last 64-bit chunk, I'm setting a flag, okay, which allows me then to make a decision, okay, because could it be the case that I would want to do thing A if the carry flag is set and thing B if the carry flag is not set? Okay, potentially, yes? Okay, well, how do I make a decision based on the carry flag? Well, making a decision is code for branching, yes? Okay, well, what kind of branching instructions have we used? Huh? We've used branch and link. Okay, that one's special because it's related to the link part is the breadcrumb thing. Okay. What other branch instructions have we used? We've used the unconditional branch, which was just B. Okay, but what about the conditional branches, the ones that made decisions? Which ones have we used? We did a comparison followed by B dot something. Okay, what were the dot somethings that we've used? No, the condition codes.
Oh, like the EQ.
Yeah, equals, not equals, less than, greater than, or equal, less than or equal, and which exact one you use depends on how you structured your code. Okay, but all of those things that immediately follow a comparison instruction. Yes? Okay, well, there's another condition code, or actually two of them, CC and CS. What do you think those stand for?
Compare and contrast.
No, compare and contrast. Carry clear and carry set. Okay, so I could branch if the carry flag is raised or clear. Okay, all right, so let's look at how I would do that. Okay, so let's go back here. Oops, that's not what I meant to do. All right, so let me put in a few labels. Okay, so let's decide what I want to do if the carry just so happens to be set. Okay, for sake of demonstration, let's put some strings in here. Okay, so I just made two strings, carry is set and carry is not set, and I'm going to print them in the appropriate cases. Okay, so let's say branch on carry set to carry set. What happens if the carry is not set? Where do I want to go? I want to go to carry not set. Okay. And then on this one, I need to branch to end at the end of it. Okay, to skip over the carry not set part. No, because if this does not execute, that means the carry is not set, and therefore it just goes straight to here, right? So I don't have to do a double conditional. I could, but it's not necessary. Okay. Okay. What do I want to do if the carry is set? I want to print carry is set. Okay. So how do I print that? I need to do what? Yeah, I need to load into X0 what? String one's address. And then do I need to load anything else into any other registers? No, so I can branch and link to what? Either printf or I'll just use puts because we're not actually doing any formatted printing. Okay, and then go to the end. If the carry is not set, then what am I going to load? The other address. And do I need to have a B end here? No, because that's the next instruction. Okay. All right, so let's assemble and run this and see if it works correctly. Okay, carry is set. Okay, now let's think about that. In fact, let's go back into GDB and make sure that it should have been. Okay, so this is right before I do the addition. The carry and the zero flag both happen to already be set, okay? And if I do the result of this arithmetic, what did we say is going to end up in register 5? Not 1, but 2. Because what's happening here is I'm doing -1 plus 2 plus the carry flag, right? So what's -1 plus 2 plus 1? 2, yes? Okay. And so if I step, then of course what's in register 5 this time? Okay, 2. Okay, so just because the carry flag happened to be set. All right, now the carry flag's after the operation, which flag is set? Did our operation just generate a carry? Yes. So accordingly, the carry flag is set. Did our operation generate an answer that was 0? And therefore the 0 flag is no longer set. Yes? Okay. And so if I'm about to do BCS to carry set, is the carry set flag set currently? Yes. So this branch will take place. And where does that take me? To the carry set part, where it's going to print, branch to end, and terminate. So did I ever print that the carry was not set? No, because I skipped past that part. The carry was set. Okay, yes? Okay, so this sort of begs then maybe one other question, which is how could you clear the carry flag if you needed to? Right? So, like in some processors, there actually is an instruction to clear the carry flag. Just bam, done. There isn't on ARM, okay? And so how we would have to get at it is, let's see, let me remind myself what that instruction is called. It's not the thing that you would think it is. Yeah, okay. So what I can do is, and let me just add this into our program. And I'll do it right here after the add operation. And I'm going to move, and I'll put it in X6, although I think I only actually need to put it in W6, but whatever. And it's called NZCV is the order. Okay. Okay, so let's assemble that. Oh, right. Okay, hold on. What is there's a different instruction for this. That's right. It's MRS. Okay, so move status to register. And that should be an X register. Oops. Okay. So now if I go into GDB, okay, I'm about to execute this MRS instruction. What happens to be in register 6? Whatever, right? Okay, after I execute this instruction, what happens to be in register 6? Okay, 2 followed by a bunch of zeros. Okay, now let's think about where did I have this instruction? I had it immediately after an arithmetic instruction that raised the carry flag, but not the zero flag, the overflow flag, or the negative flag. So 3 of the flags were down, 1 of the flags was up. Okay, and it just so happens, okay, that the those flags are in positions 31 down through 28 of the processor status flag register. Okay, so let me just write this on the board, right? So I have, and bit 31, by the way, is the 32nd bit because what's the lowest bit usually? Bit 0. Okay, so if I have, and the order is NZCV, if I have a 1 here and a 0 in those 4 positions, what is this binary number? 0010 corresponds to 2, which, look, that's why it's a 2 in that final spot. Okay, so the last nibble, okay, which is the last 4 bits of that number, is the N, Z, C, and V flags in that order. Okay, so what would I want to do if I wanted to clear that flag? Well, what did I just do with this instruction? Okay, what did the instruction MRS do? It took the NZCV flags and moved that data into X6, right? So I took status flags and put them into a regular register. Do you think I could maybe go the other way? So let's say I wanted to clear all the flags. What should I put in X6 and then move over? What about if I just put 0? Wouldn't that clear everybody? Yeah, okay, so let's try that. All right, so let's do this. Let me just use X7. So let me move X7 0. And then if I go, you guys are going to love this. Right? So if I want to go from the status register to a regular register, which instruction do I use? MRS. If I want to go the other direction, which instruction do I use? MSR. Okay. Do not try and do this at 2 in the morning because you will get the R and the S backwards. Right, men? Doing things at 2 in the morning is bad. Okay. All right. So what's going to happen is I put 0 into register 7, and then I'm going to move that or copy it to the status register flags, which is going to clear all of them. Okay. Yes. All right. So let's see if that works. So now, did a carry occur when I did my addition? Yes. But why did it do carry not set? The addition did generate a carry, correct? So why did it print carry not set? Because what did I do right here? I cleared the carry bit. Right? So the addition set it correctly, but then I went and destroyed it. And so when it came down to the branch on carry set, well, the carry wasn't set anymore. And so, okay, let's move on. Because I was an idiot. I did it deliberately here, right? So my point, though, is that you can change the status flags manually, but do so carefully because you could F things up. Yes? That's interesting. Okay. Now, in our case, loading 0 cleared all of the flags. Let's say that I wanted to set all of the flags just for giggles. Okay. What would I need to load in? Not 1. I want all 4 bits to be 1. So what is that in hex? That's F. Except which nibble do I want it to be in? The 8th nibble from the bottom, okay? Which means it's in positions 28 through 31 or 29 through 32, depending on if you start with 0 or 1, okay? If I did it as is, it would put that that F here. Do I want the F there? No, so I need to shift it. How many positions do I need to shift it? It starts in 0 through 3, but I want it to end up in 28 through 31. So how many shifts is that? Well, 28. Yes? Okay. So I want to do a logical shift by 28 positions. Oops. Let's see. So I can't do that. So let's do move Z. Oh, sorry. It's because I forgot to put that's in hex, and I forgot to put a 0x in there. Unexpected characters at operand 2. Okay, so I think we need a Z there. Oh, yes, that's right. Okay, so what I have to do is this. I have to do F000, logical shift left by 16. Okay, so let's think about why that will work. So originally what I did was I put the F in the lowest nibble and then said, okay, I need to go 28 spots over, but the logical shifting always has to be a multiple of 16. Okay, that's actually nice because it means that we can encode those shifts with 2 bits instead of 4 or 5, actually. No, 6. So it saves us on bit encoding. Okay, so I have to use my head in order to get the bits in the right spot. Okay, so where do I want this F to end up? 16 bits to the left of it. Okay, so that F is going to be all ones, shift it 16 bits over, and I'll get an F in the position that corresponds to my status flag stuff. Okay, and then let's go through in GDB and see that this works. Okay, so what's in register 7 right now? Gobbledygook. Okay, right after I do my move Z instruction, okay, what's in the registers now? What's in register X7? Is the F in the appropriate position? Yes. Okay, so if I move this into the status register, which is the instruction I'm about to execute, what should I see here for the flags next? All of them should be set, correct? Because I'm putting a 1 in each bit position. Okay, negative, 0, carry, and overflow should all 4 get set. And look at that. Overflow, carry, 0, and negative are all set. Now, I find it mildly irritating that, what's the order that GDB prints them? Yes, it is reversed from the other way of writing it. I don't know why it does it that way. Okay, but it does. Okay, so whatever. But point being, the positions of those things are the negative flag is in position the 31st position, 0 is in the 30th, carry is in the 29th, and overflow is in the 28th. Okay, so you have to, like, if you wanted to set some of them but not the other, right, you have to be careful about the order to put the right bits in the right positions, or else you're going to have a bad time, right? If you pizza when you should have French fried, you're going to have a bad time. No? South Park? Okay, just making sure. Okay. Okay, so yeah, so the cheat sheet is useful. So pay attention to the cheat sheet because it will save you. Okay, so the other upshot, and it's a good thing that I made this mistake because it means that I can point it out, that the logical shifts always must be multiples of 16. So you really have 4 options for the shift. 0, which is to say don't do any shifting, 16, 32, and 48. Okay, that's good because how many bits does it take to encode those 4 options? 2 bits, right? Because 4 options would be options 0 through 3, right? How many bits does it take to encode that? 2 bits, right? 1 bit gets you 0 and 1. 2 bits gets you 0, 1, 2, and 3. Yeah? Isn't this great? Yeah? Okay. So, all right. So I'll make some adjustments to Canvas and come up with yet more devious assignments for you guys to suffer through. And then on Thursday, where we're going to go next is we've done some printing with strings, right? We've printed them. Okay, great. But what did we do when we were in C? Didn't we also do some processing with strings where we like did stuff to them? Yeah, like we computed their length and maybe we changed letters or we did some sort of like encryption routine. How do we do that in assembly?
I don't think we need to.
I think we do.
That's what C's
Yeah. So we'll start talking about string processing on
I'm gonna try to
Thursday.
do this.